All right.
Salted yesterday.
I know. Carbonated frozen yogurt turns out to be the big taste sensation with the younger backpacking crowd. Yeah, it's sweeping the nation for backpacking scouts. Very popular, okay? Now, again, you know it's going to happen. Works great at our low altitude stations, but we're definitely having some problem getting enough carbon dioxide to dissolve at certain of our many wilderness ice cream outlets. Sure, Pop Rocks.
You know, so carbonated Jones apple candy is so tasty.
Okay. So here's what we need to do. We need to understand what causes how much solute we can get to dissolve. We have talked about a couple of different ways to measure concentration. There are several others that we're going to talk about. But we also need to start...
I just want you guys to know that the Cookie Club is having their meeting on Tuesday the 18th, and that today is advisory schedule. This will be the only announcement for today. We're not doing an actual bulletin today. So just so you know, there is Cookie Club that's going to be held on Tuesday. I want to put that out there since there's no school on Monday. And I need to be clear that today we're on the advisory schedule. So if you need to know your advisory schedule, they're still posted throughout the school campus, or you can check with someone right away after second period report to advisory. Thank you, everyone. Have a great day. There will be no bulletins, so if you have questions, come on out.
Okay, anyway. There are several different ways that we can measure concentration that are going to help us get at how much of one substance can we get to dissolve into another. Okay? So we've talked about a bunch of these, right? The one we've just learned about, moles of solute divided by kilograms of solvent, we call that the molality. We've also used the molarity, moles of solute divided by liters of solution. Okay, total liters of solution. Now, there's another one that we've used in reference to pressure. We call that the mole fraction. Okay? Moles of solute divided by total number of moles. That's like the moles of one gas divided by the total number of moles of gas, or the pressure of one gas divided by the total pressure of our container for gases. This is the mole fraction. Moles of solute divided by total number of moles in the solution. The final one that we use is typically a sort of percent by mass. Okay? The mass of the solute divided by the total mass of the solution. So the question that all of these measures beg, and they are all useful in different contexts, is how much of one thing can you get to dissolve into another? Okay? What is the maximum concentration that you can get? Okay? How much sugar can we get to dissolve into our water? How much carbon dioxide can we get to dissolve in the frozen yogurt mixture? Okay? These types of solubility questions are important because it's going to drive how carbonated we can make our frozen yogurt. So, what we want to look at is what kind of factors affect solubility. And one of the big ones is structural effects. How similar are the attractive forces? This is where our saying like dissolves like come from. Okay? So we can put a non-polar solvent, carbon tetrachloride, in here. And what we're going to do is we add just a little bit of colorant. It's a non-polar colorant. Okay? So you stir it up. This is non-polar carbon tetrachloride. Okay? And then they're going to go ahead and pour some water on top. Okay? Water is less dense than carbon tetrachloride. The water floats on top. You can shake it up, and it separates back out. They have very different polarities. Highly nonpolar. Okay? Water is very polar. Now we're going to add some hexane. This is hexane. Nonpolar but less dense than the water. We form these different levels. Watch what happens when they shake it up.
When the test tube is vigorously shaken, the two nonpolar liquids
Oh, I
form a
guessed
single
it.
layer at the bottom of the test tube.
These are both nonpolar. Things that are the same nonpolarity mix well. Things that have similar polarities mix well together. If you have two polar substances, they'll mix well. If you have two non-polar substances, they'll mix well. This was what drove our chromatography, right? Like dissolves like. We had a polar molecule, a polar dye, and we used a polar solvent, that is a lot of water and a little bit of the isopropyl, the dye moved out. When you loaded a non-polar dye or a less polar dye, it wouldn't move with the highly polar mixture. You had to up the concentration of the isopropyl alcohol to drop the polarity until it was closer. Things that have similar polarities will mix well together. So, mixtures that have similar polarities will have high solubility. Sugar is a polar molecule. It has a lot of hydroxides on it. It will dissolve very well into water. Okay? Acetic acid, ethanoic acid, has a OH molecule. Okay, has a hydroxide on it. It will dissolve very well into water, but it won't mix with oil. Oil is a long chain hydrocarbon, non-polar. Okay, water and oil don't mix. Vinegar and oil don't mix. You can do some interesting things if you make the drops tiny, 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 emulsify the solution. Okay, so the drops are so small they can't recombine together. Then you can get things to mix in that way. But we say like dissolves like. Well, there's always a little bit that sticks to the sides of the container, or these sort of drops are just sort of hanging out attached to the sides of the container walls. They're not all the way across, probably.
So if you wanted to make like oil and vinegar and you didn't want to make it
Separate?
you could add little drops of oil slowly.
Well, yeah, I mean, that's possible. You need the drops to be really small, like milk, right? Homogenized milk. The droplets of fat in the milk are they're shot through tiny nozzles and make really tiny little drops, globules of fat.
So
that's why they stays mixed together. Otherwise, when you get fresh milk from a cow, the milk fats, the cream rises to the top, and it separates from the water, and they don't stay mixed well. So yeah, you can, by controlling the size of the droplets, or using an emulsifier. Emulsifier is a chemical that has half of it is non-polar and half of it is polar. That's a soap. That's soap. Soap is basically has a long non-polar tail and a little polar head. And so part of it can stick in the water, part of it will stick in the oil, and it'll help the two mix together.
So we can put soap in oil and vinegar?
Yeah, if you put soap and oil and vinegar, they'll mix really well. You do this in the sink all the time when you're washing up. If you have a little bit of oil in a pan, you pour some water in it, you can see the oil float on the top. You add a drop of soap and it goes, because it all starts to mix into the water. Okay. Tea might work. Might have some emulsifiers in it. Okay, so one thing that is the structure. Things that have similar polarities will have high solubilities. They'll mix well together. For gases, pressure turns out to be super important. The higher the pressure, the greater the solubility. And this is going to be important for our carbonation, okay? Your can of soda is carbonated because they've taken water with some gas molecules dissolved in it and they put it under high pressure, which increases the solubility of the gas. Okay? When you open the top of the can, it goes psh. That's the little bit of carbon dioxide at the top coming out that kept it at a high pressure. Now the rest of the time, the carbon dioxide is slowly precipitating out, essentially, of your solution. Right? A carbonated beverage is just a water that has carbon dioxide pumped into it. Okay? Well, yeah, you can have sugar or things like that. But like soda water, like sparkling water, it's just carbon dioxide that's been pumped into the water.
Does that make it weird when you drink water? Does it make it weird when you digest it or something?
No, it doesn't fundamentally change that. It all pretty much comes out relatively quickly. Now, so we have, there's an equation that you can describe this. It's very simple, right? Pressure, concentration, some proportionality constant. Increasing the pressure increases the concentration of gases. Decreasing the pressure decreases the concentration of gases. K is just some constant, some number that's probably going to change with the gas and some other things. But it's not a, it's just a proportionality constant to make the units and the conversion work between pressure and concentration. Yeah, they have to give you the K or information to figure it out. But we typically don't do a lot of calculations with this. It's just something you need to understand the relationship between pressure and solubility for gases. Now the big thing that affects solubility, and many of you have probably done this, have you ever made rock candy? You were in elementary school, okay? And so you heat up water and you dissolve sugar into it, and then you let it cool down, and you stick a string, and crystals slowly over the course of time start to form, okay? So temperature is the big factor, okay? The issue with temperature is that in general, if you increase the temperature, the solubility of most solids goes up. So the solubility of most solids goes up with increasing temperature. You can get more salt to dissolve. You can get more sugar to dissolve. There are a few substances where the solubility goes down with increasing temperature. And one of the big things that's important is that the solubility of gases goes down with increasing temperature. So that's why if you have a warm Coke, it is more likely to fuzz up, right, and foam all over the place as the carbon dioxide comes out all at once than if you have a cold Coke. A cold Coke, more carbon dioxide can stay in the solution, so there's less of it rushing out of solution all at once.
Why it comes explode
As it starts to freeze up, there's less and less liquid for the gas to be dissolved into, and the pressure goes up. More importantly, what happens to water as it freezes? What happens? It expands, which is unusual because the ice crystals have a larger volume than the water itself. And that's the main driver. Yeah. I'm sorry, say what? I'm not sure. That's a good question. Why does the sodium sulfate? I'm not sure. I honestly don't know.
Is it just a solid in the bottom of the water? And then as you raise the temperature, it dissolves?
Well, then it should be flat. I mean, but see, this is the solubility decreases. I don't know. We should look that up. We'll have to look up why the sodium sulfate line starts right there. I don't know if it's a misprint on the graph or some other reason I haven't thought of. I can't think of a reason why it should just start at 30 and go down from there. You would think that at the very least they would leave the line flat or something like that, but that wouldn't make sense either. So notice some substances like sugar, right? Very soluble in water, nice polar molecule. Some ions are highly soluble and have a really big change. Some of them are relatively flat. It's all just all kinds of crazy structural effects based on the attractive forces between the water and the substance. One thing to note here is how the solubility is expressed. Grams of solute per 100 grams of water. Okay? So this is a typical sort of graph, grams of solute per 100 grams of water. We can use this to do predictions on how much stuff will precipitate out, how much we can get to dissolve, all kinds of fun stuff. Soluble means that it will dissolve into water. Breaking apart is not necessary. Sugar doesn't break apart when you dissolve it in water. It stays as a whole sugar molecule. Yeah, it dissolves into the water as individual molecules. Yeah, the intermolecular bonds would break. Yep. Okay? So one way that we typically use this graph, and you have this graph on your paper, is a sort of question like this, which would say that 200 grams of water are used to make a saturated sugar solution at 60 degrees. How much sugar will precipitate out if the solution is cooled to 20 degrees? So at high temperatures, right, you can see the sugar at a high temperature, 60 degrees. You can look up and say, how much sugar can I get to dissolve? You can calculate, get that number, okay? then you can get that number at 20 degrees.
Oh, 200 grams.
Right, 200 grams of water. But we'll deal with the 200 in a sec. So what I would do is I'd look up at 60. And I would say, okay, that looks to me to be 285. Okay? I'd say 285 grams of sugar per 100 grams of water. Yeah, this is your example. I'm just going to sort of, because we have a little bit of limited time, I'm going to walk through it. Then I would do the same thing at 20 degrees. At 20 degrees, I'd say, yeah, that looks like maybe 190, maybe 200. It's going to be approximate. Okay? So here is my 190 grams per 100 grams of water. So what's the difference? If I start here and go down, how much has to precipitate out? 285 minus 190 means 95 grams for every 100 grams of water. But I have 200 grams of water, so essentially I'm multiplying that 95 times 2. I would have 190 grams precipitating. Okay? So this solubility chart allows me to say how much will dissolve at given temperatures, and allows me to do calculations where, well, how much do I need to add, or very commonly, how much will precipitate out. So I look on the line, I find the difference between the two. I have to take into account how much of the solution I'm making, typically expressed as how many grams of water am I using to make the solution. In this case, 200 grams, 200 milliliters. Now, the volume of the solution is actually going to be different because, of course, I've added a bunch of sugar. I looked on the graph. I went 60 degrees. I saw where it hit the sugar line, and then I went over here and made an estimate about what that value is. That value there looks to be about 285.
Okay, and then what's the other one?
I went at 20 degrees.
Oh,
Because it's cooled down to 20 degrees. I went to 20 degrees and did the same thing.
Okay, and then that gives you the average.
So I didn't do the average. I said, okay, at 60 degrees, I dissolved 280. When I cool it down, as I cool it down, it holds less and less sugar. So sugar literally begins to precipitate out as a solid. There would be sugar crystals growing on the side of the beaker or in the little string I dangled down in the middle. This is exactly how rock candy forms. As the solution cools down, and then as it starts to evaporate, you're at the saturation point, and so what happens is it literally begins to crystallize out to grow as a solid in your solution. Now, for this setup, between 60 and 20, you have to have 95 grams precipitate out. As it cools down, 95 grams will precipitate out per 100 grams of water. We had 200 grams. That gave me the 190.
Oh, okay. So when you do it, the water you end up with is sugars.
Yes, the water you end up with is sugary. It's saturated with sugar, actually. The water you end up with is still saturated with sugar. Saturation is when you're exactly on this line. The saturation point is, hey, at this line, that's as much as I can normally get to dissolve. It is possible to have a super saturated solution. If you have a clean container where there's very little places for crystals to start to form. What's called the energy of nucleation, the amount of energy it takes for the crystal to start growing, there's a certain amount of energy that takes. So if your container is very clean, there's no little cracks or defects that can help the crystals form, it's possible to be above the line in what we call supersaturation, where you have more dissolved than you would normally be allowed to have. And so a lot of times if you shake it or jar it, it can start the crystallization process. Yeah, it can. That's actually, for solids and ionic compounds, a much more complex process. There's equilibrium interactions between them and all kinds of crazy stuff. the other thing that affects all this is these are all non-volatile compounds. None of these have any significant vapor pressure. And that has a factor as well. And so what we need to think about is what would happen if we wanted to actually mix a volatile substance, two volatile substances together. We have to be able to think about a mixture where both of the components have a vapor pressure. For instance, water has vapor pressure. And if you wanted to mix in alcohol, like you wanted to make, say, alcoholic frozen yogurt, you would have to be worried about the additional vapor pressure from the alcohol. That would change its freezing point, its boiling point, the saturation, all these kind of phase change properties. When you start to mix substances together, makes a difference. Okay? So we've got this great carbonated beverage for the kiddies. Now the troop leaders are all looking for something to take their minds off the fact that they're, have to deal with these little kids all day. So some alcoholic frozen yogurt might be just the treat for them. So what we have to deal with is how does vapor pressure change? How do we deal with vapor pressure? Because that's really what drives, say, boiling point and freezing point. Is really going to have a big impact on those things. How do we deal with vapor pressure when we have a mixture of substances, when we have a solution? Okay? So what we have here is we're going to look at two different substances and then a mixture of them and look at what their vapor pressures look like. Okay? This is another way to measure vapor pressure. We measured vapor pressure using a Dalton's law of partial pressures thing, but there's a simpler way to do it that involves using mercury and manometers and fun stuff like that. Basically, the equation that that's going to break down is that the total vapor pressure of a solution depends on the mole fraction times the partial pressure of the component. Okay? So if you have a mole fraction that is 1, if you have a pure substance, then the vapor pressure of the pure substance is the total vapor pressure. But if you have a mixture, if you have several different components, okay, like we're going to see right here, this is hexane. We put hexane in here, and we squirt it in the mercury, the vapor pressure that's formed, the vapor that's formed pushes the mercury up. That's pentane. This is it's a rubber septum that seals itself after you take it out. Okay? So we squirt pentane into here, and you can see that the pentane vaporizes and produces a gas, the vapor, and so we can measure the vapor pressure. This is a mixture, a 50-50 mixture of the two. Okay? So 50-50 mixture of hexane and pentane. So you can see hexane, okay, pentane, and the mixture. So there's our hexane, our pentane, and the mixture, okay? You can see that the mixture is essentially right in the middle of each one because this is a 50-50 by mole, 50% pentane, 50% hexane. Now, if you have more of one than another, you end up getting a skew, right, in the number of moles. Essentially, if you plotted the vapor pressure of one substance and the vapor pressure of another and drew a straight line between them, and you put the mole fraction across the bottom, you would be able to predict the vapor pressure. Key is that the total vapor pressure is equal to the vapor pressure of one substance times its mole fraction plus the vapor pressure of the other substance times its mole fraction. And you do that for all the substances that have a vapor pressure.
Is P vapor pressure?
Yeah, P is vapor pressure in this equation. No, I don't think so. I don't think you need to worry about mole fractions changing over the course of the thing. They usually would just say, that would be really tricky. You would probably just say at the end, what's the thing? And you would have to do a stoichiometry to calculate what happened. That's possible, but unlikely. This would be a good extra credit problem, though.
Why is there a little circular thingy above the second?
They're standard vapor pressures. The little circle thingy, which is called a knot symbol, because it's actually, that's a degree symbol, but I'm using it in representation of what we call a knot symbol, is actually just tells us standard conditions. All right, so one more example here. We have 30 grams of ethanol is mixed in 100 grams of water, okay, which would give us something like a 60 proof frozen yogurt. Given that the vapor pressure of ethanol is 59 millimeters of mercury, the vapor pressure of water at the same temperature is 23.8 millimeters of mercury, what's the vapor pressure of the solution? So we know that the total vapor pressure is the sum of the vapor pressure for each component, okay, times the mole fraction. So you take the vapor pressure of the ethanol times its mole fraction, take the vapor pressure of the water times its mole fraction, and you add those values together. So to do that, we need to know the molar mass, and we need to find the number of moles of ethanol and the moles of water. So take a minute and do that. Step one, how many moles of each one of those do we have? How many moles of each one do we have? Calculate the mole fraction, multiply it by the vapor pressure. All right. Are we done? I'm done. Take the grams of ethanol, divide by the molar mass, gives me moles. Do the same thing for the water, 100 grams, divide by the molar mass, moles of water. I need to add those together. And I'm going to take each one divided by the total. And that tells me that essentially the mole fraction, the percent of the moles that are ethanol is 0.105, so 10.5% of the moles are ethanol, and 89.5 for water. Now I take the vapor pressure of the pure substance times what percent of the mixture, what the mole fraction of the mixture is for that substance. 59.0 times 0.105, 23.8 times 0.895. This is the weighted average. This is just like what you would do for if you were thinking about the atomic masses from the periodic table. You take the percent abundance times the mass of each component. This is a weighted average calculation. Okay? Now, one thing to really think about here is that if you have a mixture, the vapor pressure of the solution is different than the vapor pressure of the pure substance. Okay? And so you could try varying that mixture and see how that vapor pressure changes. That's one thing, that you might think about. For the lab I'm going to hand out. You could also try different substances when you have different percentages for different substances, temperature, all things you might think about, things that affect vapor pressure. So the total pressure, 27.5. So here's a question. Would this mixture boil at a higher temperature or a lower temperature than pure water?
Higher elevation. It's higher. Because the freezing point is lower. Freezing point is lower.
So remember when we talked about boiling point elevation and freezing point depression? That was all based on non-electrolytes. Okay? Boiling is going to be driven by the vapor pressure. The vapor pressure of this mixture is higher than the vapor pressure of regular water. That means the boiling point will actually be lower. Because the vapor pressure of the boiling point of the ethanol, right, has actually been raised, but the boiling point of the water has been lowered. This is where it's tricky, because we have a mixture of both two substances that both have vapor pressures. Okay? So this is going to boil at a lower temperature than water, but at a higher temperature than ethanol.
Why would it increase the vapor pressure
So boiling is when the vapor pressure equals the atmospheric pressure. So we will equal the atmospheric pressure at a lower temperature because the vapor pressure is going to start at a higher point. Okay? All right. Okay? Fairly straightforward calculation. This is something you might see on a test or a quiz. You've got a review sheet that I've handed out. You've got a worksheet that's due. And I have one more piece of paper I'm going to hand out to you in just a sec. But this is it. That's the end of chapter 11. This is the end of stuff that we need to know for the test. Okay? I don't know, but I just lost the game. Did anybody look at the first letter of each word there?
Oh my gosh.
You guys missed yesterday's. You guys didn't even catch yesterday's at all. Did you notice it? There was a little letter here on each slide. Anyway.